of the oxygen is burned to silicon, you're in the last day in the life of a star. Because remarkably, it is so hot at that point that all of the silicon in the center of the star, many thousands of times the mass of the Earth, burns to form iron in one day. And at that point, it's rapidly burning and struggling for existence, because once it's burned to form iron, it's on its last death throes. Because iron can't burn to form anything. Iron is the most tightly bound nucleus in nature. And so once that happens, there's no more fuel. When all the silicon is burned to iron, suddenly the star realizes there's no place left to go. And that interior of the star, which has been held up by the pressure of nuclear burning, collapses. And that whole collapse happens in 1 second. And when it happens then, it spews out, there's a shock wave, and the shock wave, like an onion, spews out all of the elements that were created during the life history of a star. The carbon, the nitrogen, the oxygen, the iron. And that's vitally important, because every atom in your body was once inside a star that exploded. In fact, as I said, and I think the quote is in there, the atoms in your left hand probably came from a different star than your right hand, because 200 million stars have exploded to create the elements that make up your body. Because in the Big Bang, only hydrogen, helium, and lithium were created. That's not important. Well, lithium may be important for some people in this room, but the rest of, but carbon, nitrogen, oxygen, all those other things are the stuff that we depend upon. And those weren't created at the beginning of the universe. The only place they were created were in the nuclear furnaces at the center of stars. And the only way they could get into your body was if the stars were kind enough to explode. So as I said, and I threw it in a throwaway line, but it's become a big line, forget Jesus. Stars died so you'd be born today. Okay? And it's true. You are stardust. It is literally the most poetic thing I know about in all of science. You are star children. You would not be here. Just think about that. Every atom in your body has experienced, maybe more than once, the most violent explosion in the universe. They had to, because they couldn't have gotten into your bodies otherwise. And 5 billion years ago, a supernova exploded in our region of the galaxy, compressing gas, triggering the formation of our sun. And it was those elements that came from that supernova explosion, mixing with the gas in the solar neighborhood, that produced everything we see in this room, and all of the rocky planets and everything. You are connected to the cosmos in an intimate way, and your atoms have been around for billions of years, changing their form until 5 billion years ago. They came in together in the current form they have, and they haven't changed since then. And they're in your body.
So this is a picture of the history of the universe. This is the beginning of the universe. This is today with lots of galaxies. At the earliest moments, when the entire observable universe was contained in the region about the size of an atom, that's right there. We predict, based on our ideas of particle physics, that something very strange happened back then. At that instant, the energies were so immense that the universe underwent something called a phase transition, like when water freezes to ice. And in fact, if you're in on a day when it suddenly gets cold very fast, there's water on the roadway, it can be below 0 Celsius and it still won't have frozen. Okay? Because if the temperature changes very fast, the material gets stuck in this metastable state, the liquid state, and then suddenly it freezes. When it does, it emits a lot of energy. It turns out our ideas of the early universe are almost identical. We think that as the early universe expanded, it got stuck in a metastable state. We call that period inflation. And energy got stored in empty space. Back then, when the universe was a billionth of a billionth of a billionth of a billionth of a second old. Okay? A billionth of a billionth of a billionth of a billionth of a second after the Big Bang. We speculate. We theorists can speculate about whatever we want, and no one, it's easy to do. But we predicted that that would happen. The universe would get stuck, and when energy gets stuck in empty space, the universe starts to expand incredibly fast. And the prediction was that in a billionth of a billionth of a billionth of a billionth of a second, the universe would expand in volume by a factor of 10 to the 90th. It would go from being smaller than the size of an atom to being about the size of a soccer ball. In a billionth of a billionth of a billionth of a second. Okay, fine. But during that time, when the universe is expanding, the energy densities are incredibly high, and gravity, which is incredibly weak, we predict that at those incredible densities, quantum mechanics is important, and it may even be important for gravity. And space-time itself may begin to fluctuate by quantum fluctuations. Those quantum fluctuations produce disturbances in space-time, but the universe is expanding so fast that those get frozen in. Instead of vibrating, they get frozen in because they get stretched to be larger than the size of the visible universe, namely their period. So they would like to oscillate like gravitational waves, but the universe stretches them so their period becomes longer than the age of the universe, and they just sit there. So you have these quantum fluctuations in early time that get frozen in, and then after inflation ends, they're observable as gravitational waves. Now the first ones to get stretched get pushed out the longest. The last ones to get stretched just before inflation ends come and start vibrating first. But as gravitational waves start vibrating as the universe expands, they dissipate their energy. So the shortest wavelengths, gravitational waves, dissipate their energy, and by the time the cosmic microwave background is formed, they've gone away. But the longest wavelength waves, the ones that are just beginning to oscillate, when the universe is 380,000 years old, what do? Well, remember, the cosmic microwave background is formed when the universe becomes transparent, the last instant before protons capture electrons. So just before it becomes transparent, you have these free electrons sitting there. If a large gravitational wave comes by, it'll shrink space in one direction and stretch it in another. And what that means is the electron will see a hotter universe in one direction and a colder universe in another direction. And it will scatter that radiation to us, and we'll see it today, and that radiation will be polarized. It'll be stronger in one direction than another. Many of you have polarized glasses. And what polarized glasses do, light can vibrate, and electromagnetic fields can vibrate in many different directions. And the polarized glasses cut out one direction of polarization that comes from scattered radiation on the ground, which is why you can see through, if you're a fisherman, you can see through the water better, because that polarization gets canceled out. But what we predict is if there were gravitational waves created at the beginning of time, they'd produce a very particular kind of polarization in the radiation. And what this experiment in the South Pole was designed to do was look for this kind of snake-like pattern of polarization. And actually, no one thought anyone would see it. 4 months ago, the experiment reported a result. And here's the actual data from the experiment. You see exactly what we predicted. This snake-like pattern of polarization, of twisting polarization in the cosmic microwave background. There's cold spots and hot spots, the ones you saw before, but on top of that we've shown the polarization, the direction, if you wish, of the electromagnetic field that's causing that radiation to come to you. We can measure it in this detector, and it was exactly what was predicted if inflation happened in the early universe. Now, we don't know if it's really a gravitational wave from inflation. In fact, there's a lot of discussion, because there are other things that could produce this kind of, like anything that's very sensitive, there's lots of noise that can produce it. It turns out there are polarized dust grains in our galaxy that emit polarized radiation. And some people have argued that these people may be seeing is just some foreground effect from the radiation coming through our galaxy. But it looks identical to what we would predict. And if it really is a gravitational wave from inflation, the consequences are profound. Because not only does it mean that for the very first time in history we've detected gravitational waves, we see them literally in the image. But this image comes to us not from 380,000 years after the Big Bang, when the hot spots and cold spots came from. But the polarization is due to gravity waves that have been traveling from the time the universe is a billionth of a billionth of a billionth of a billionth of a second old. If this is really true, what this is an image of is an image of phenomena that took place at essentially the Big Bang. And that changes everything. It increases by a factor of 10 to the 49th our ability to go back in time. More than any era in the history of humanity, it allows us to jump back and test what the universe was like when its physical size was less than the size of an atom. And we can test physics that we thought we'd never be able to probe, ever, empirically.
How do you define nothing?
Well, that's a good question. And in fact, I would argue that the scientific definition of nothing is a little more careful than the theologians. And the first definition of nothing might be what it would have been in the Bible: eternal empty void, empty space, darkness. And I think for many people that would be a good definition of nothing, until I tell them that something can come from that. Because in the real world, in the world of physics as we now understand it, empty space isn't so empty. It's a boiling, bubbling brew of virtual particles that pop in and out of existence in a timescale so short you can't see them. And in fact, that kind of nothing, due to the laws of quantum mechanics, is unstable. It will always produce stuff, naturally, by the known laws of physics. And so, for some reason, people, when I tell them that's nothing, and they say, well, that can't be nothing because that can create something. So
Right.
there's space there. What about, nothing really has no space. And then I tell them that if you apply the laws of quantum mechanics to gravity, you can actually create universes and spaces where there were no spaces before. And so we keep going on and on and on. And I like to say that theologians say that my definitions of nothing are not the right ones, but I like to say that they're experts at nothing.
Wow.
What I mean by empty space is something where there's no measurable stuff. You take some region of space, and you get rid of all the particles and all the radiation, so there's nothing you can measure there. But what is really one of the greatest discoveries of the last century, and I'm happy to say I played a role in it, it's astounding that we've discovered when you take that empty space, it weighs something. It actually has energy. In fact, most of the energy of the universe resides in empty space. It's the biggest mystery in science. We don't understand why it is, but 70% of the energy of the entire universe resides in nothing.
How do you weigh empty space?
Well, you weigh it using gravity. Gravity's the way I
Oh.
can weigh you using gravity. I wouldn't do it now, but I could.
Yes.
and it turns out the really strange thing is if you put energy in empty space, it's gravitationally repulsive. Instead of attractive. Everything else in gravity is, as I like to say to high school students, gravity sucks. We always know gravity pulls, it never pushes. But if you put energy in empty space, it's the only thing you can show using the equations of Einstein and general relativity that it's gravitationally repulsive. It's like anti-gravity. And what we've done is weigh the universe and see that, in fact, the expansion of the universe is speeding up, not slowing down, as any sensible universe would do, because gravity would normally slow the expansion of the universe. And the big surprise about 10 years ago was the discovery that the expansion of the universe is getting faster and faster and faster. And the only way to understand that is if empty space has energy. We don't have absolute truths in science, unlike religion. That's the reason that science makes progress, because we can change our minds. And I think that's a really important thing, that we, as I often say, if you're a theoretical physicist, the two most important states to be in are either wrong or confused. Because that means there's a lot left to learn. It's hard to imagine. I mean, given that there are over 100 billion stars in our galaxy, we now have learned that most of those stars have planets around them, so solar systems. 100 billion galaxies with all those stars and galaxies. And we also know that there's lots of water out there, organic molecules, and sunlight, which is all that was necessary for life to evolve here on Earth. So it's hard to imagine it hasn't evolved somewhere else. I find it amazing that here we are in this random planet, in this random place in the middle of nowhere, and we have, through our minds and the fact that we're graced with consciousness, been able to understand the universe to the earliest moments of the Big Bang. I think it's worth celebrating. These are ideas that are fascinating. Part of the benefit of science, we always talk about technology, and of course science is responsible for everything in this room almost. But for me, science is as important for its ideas and its impact on our culture. It's like great art and literature and music. It's what makes being human worth being human.